Okay, let's kick it off. Welcome, everybody. Welcome to this week's Tables Turned. I'm Kelly. I'm on the formation team and super excited to welcome everybody today. Today we have Philip Sue and Brian Doe to conduct this Algo mock interview. Brian is a formation alum and Phil is a formation mentor, and we're really excited to have them both here today. Throughout the event, if you have any questions, please feel free to put them in the chat. We're going to do the coding portion for about 45 minutes and then have a couple minutes for questions and feedback and really talk through the whole process, with the goal being that you walk away from this mock interview with a better understanding of the interview process and a coding question like this. We are really excited. So why don't we kick it off? Phil, I'll pass it over to you.
Great. Hi, I'm Philip. I volunteer with Formation a few hours a week. I've been a software developer and engineering manager for probably about 20 years. I worked at Microsoft for 12 years and at Meta for 8. And then I started a Seattle-based nonprofit focused on rapid testing and funded by the Gates Foundation, and worked on that for 3. I've been largely unemployed for the last 2 years, except my most recent job was working in an Amazon warehouse on the warehouse floor. So I come rusty from that coding wise, as you can expect. But I'm excited to do this today with Brian. Really happy to meet everyone.
Yeah, and to introduce myself, so I've been a software engineer for 4 days now, including today. I just finished formation. So I've met Phil a few times and we're like 8 minutes away from each other. So I think it's kind of funny, but I'm also happy to do this. Yeah, Kelly, should we just get started with the code of that? Or?
Yep, take it away.
Cool. Okay. So some context. Recently, I've been seeing Alex's posts on like system design, and he has some like geolocation stuff. That was pretty cool. So I wanted to ask you a question based off that today. And okay, I guess it's not really that fun. But if we think about an app like Google Maps, you can have locations on a map and you can do interesting things with it, like maybe see close by restaurants around you. And that's all I can think of right now. So if we replace the restaurant analogy with people instead, let's have kind of an app where you can see how many people are around you. So the challenge is you're given a list of coordinate data. So like, 0, 1, 1, 0, in whatever format you might want. It's like a list of strings or a list of subarrays, whatever. And create a class where you can store this somehow and allow a user to query how many people are around them. And maybe as a quick note, the coordinate data is kind of like grouped. It's clustered, basically, right? It's not like you get some coordinate data from the US and some from France. It's clustered in some kind of shape or whatever.
And can I ask a clarifying question there, Brian? So when you say it's clustered, you said there's a list of coordinate data representing where all the people are, right? When you say it's clustered, do you just mean that oftentimes people are clustered, or do you mean that data is organized in clusters somehow?
The coordinate points, you'll have like 0, 1, 1, 0. You won't have like 0, 1, 99, 0. So it's not like they're spread apart. They're kind of, the coordinates represent one area. And sorry, I forgot to mention. So at each coordinate point, there can either be a person there or not a person there. So that'll be in our data too.
Oh, okay. So do you mean that, so you'll have a coordinate space where you'll either have a person in that coordinate or you won't?
Yep.
Got it. And so the list will be like a preset set of coordinates, some of which have people in them and some of which don't have people.
Right.
Got it. And those coordinates can be expressed however you want, basically.
Yeah, list of strings, subarrays.
Okay, and how many people is this system on average dealing with? Like how large of a data set?
This is Bellevue, or let's do Mercer Island where you are. So yeah, about that one island.
Okay, so maybe like on the order of tens of thousands of people, basically, could be in this.
Sure.
Got it. And then what you want to make fast is the query of people near you. Do you have a fixed distance you're always querying, or do you query maybe with different distance requirements for every query?
Let's make it variable just so you can't say like it's constant even if you do a really inefficient operation.
Right. Got it. Okay, and then if the coordinates are sparsely populated, like let's say you do a very fine grid over Mercer Island, right? Mercer Island's like a few miles across, a few miles north-south.
Okay.
If you did a fine grid over that, it would be mostly very sparse, right? For maybe
Right.
40,000 residents. So would it be okay to express the list instead as just the coordinates where there are people potentially? Because that would be a data structure that would have a lot more information and deal with the sparsity pretty well? Or do you want it to be like literally you have spaces in the grid where there's nobody, but you still want a data point there?
Let's go with the latter to make, well, if you have an idea for the format, I think that'd be interesting. I thought of this more of the latter one. You can take it either direction.
Yeah. I feel like it would be easier to just track the locations of individual people, in a large list, let's say. And maybe a list isn't the right data structure, but what I mean is track the positions of all the people, in that whenever a person moves or changes their location, you can update that one place pretty predictably without having to know where they were before you can update their location. You know what I mean? But if you did that, and you wanted to make queries fast, you would probably we'd have to think through some data structures there. So I'll tell you like the dumb, simple way to do it. First, let's solve like the simple case of like inefficient, but obviously will work, right? So if you have the list of 40,000 Mercer Island residents and you track their coordinates just with each person, if you want to know whoever's near me right now, you can get my current location, get the distance that you define as near, let's say within like 300 meters, right? And then you can literally go through every person on Mercer Island doing an Earth distance calculation between their location and my location. And then you'd have the subset, right? And so that's like technically an O of N solution, but you walk through the whole thing. And as the number of citizens gets large and as the distance gets small, then it becomes potentially very inefficient to do that calculation.
And maybe query is a common operation too. So we might do it a lot of times.
Right. And so it would kind of suck to have that be like you walking through the list all the time. And I've never done geo stuff. So I'm really glad you asked this, because this is like me thinking about a problem space I know nothing about. So I can throw out terms like quad trees and stuff and have no idea what I'm actually doing. Right. So the other thing, though, that I do know, like the amateur hour thing I do know, is that distance calculations cannot just be trig calculations when you're talking Earth distance. Like you can't just do like, oh, what's your XY? What's my XY? Like here's our distance, right? In small distances, or if you're a flat earther, in either case, you can use trig to calculate. You can calculate that distance, right? But my understanding is that most people doing Earth distance don't do that. They do the literal spherical distance between 2 points on the Earth, because like the distance from here to like Paris would be a good example. If you literally XY'd that using like lat long, you would get the wrong answer for how far. And you would be off by like dozens, if not hundreds of miles, right? So
to keep this kind of coding base, let's just say we are on flat Earth.
Okay, great, perfect. I'll subscribe to that YouTube channel and we'll do flat Earth. the like reason that I mentioned that, however, is that the Earth distance calculation for a spherical distance makes the linear walkthrough of 40,000 residents much more painful than it sounds, because there's a ton of trig in that to actually get that. So that's another reason why you don't want to do a straight walkthrough of like 40,000 residents. So now we're in the territory of like, how might we do the queries efficiently? So I know I'm sure on the internet this is a solved problem. So like if I were actually literally solving this problem for you in a production code base, I would look up the node package that does the right geo querying, and I would use that, obviously, right? But this is only fun if we try to derive this from first principles. I think one of the principles might be this idea of bucketing people into location clusters, as you mentioned a little before. Like, so what might that look like? So like, let's pretend we like divided Mercer Island into like a grid that's, I don't know, 50 meters by 50 meters, right, for the whole island. And since it's Mercer Island, I'd have to say like 100 yards by 100 yards or something like this, right? And then you would calculate everybody's location and you put them in a bucket. So I might be in bucket like 42 or something like this. And then in theory, if I'm in the center of bucket 42 and we query for everybody within the distance,
Kelly,
and we're good.
Well, who is that? Someone's not muted. Oh, Matthew, your mic.
Someone is calling some helpline, right? I will dial a friend if I really need the help. So I could put myself in bucket 42, and then everybody else who's within that 100-yard sort of radius would be in bucket 42 as well. But the tricky part with bucketing like that is two things. One is you can query for different distances, right? So I randomly said 100 yards. But what if you ask me like everybody within like 500 yards? Then I'm in trouble again, right? Then I have to solve like a greater problem. The other challenge with the bucket straight up like that is I can be near the border of a bucket, right? So like, what if I'm on the very boundary of bucket 42? And then the problem is, well, I'm going to miss a bunch of people in bucket 41 that are technically 4 yards from me, but they're across buckets, right? So that feels to me like that straightforward solution won't work.
Well, I think there's a really good idea there. So you're basically, in some way, you're kind of pre-computing some data, so you can just return that if you're in the very center of something. If you're not in the center of something, it's possible, given some distance, a whole bucket is still relevant to you, but another one maybe just a part of it. And so maybe you just don't need buckets of constant sizes. In fact, if you think about it, if you had buckets of constant sizes anyway, like, your first solution you mentioned was n, just go over the coordinates. If they're all constant sizes, it's just n divided by, right? It's like, it's still n. It's on the order of n.
Yeah, you're right.
Yeah,
like
that's a good idea.
It's still order n. And the problem only gets better if you have nested buckets of different sizes reflecting common like queries you might have. And that depends a lot on UI, right? Like if you say I allow querying like Bluetooth, right? I allow querying 3 feet, 10 feet, and then it's something like 30 feet or whatever. If you have like some buckets or zoom levels, like on Google Maps zoom levels, then you might still be able to get pre-computed for all of those buckets. So I might be in bucket 42 at zoom level 3, but bucket 147 at zoom level 4, right? And then you can go to the right zoom level, query those buckets. But once again, like the problem is still reducing the, like, it doesn't really solve the problem. Like it just reduces the problem down by some linear amount based on the grid size over the Earth, right? It feels like you definitely have to pre-compute something, right? Like there's not a way you're going to go through and just compute the actual distance based on everyone.
So if you did have predefined buckets, like, I don't know, 1,000 feet by 1,000 feet, I guess your pre-computation is just like exactly how many people are there. And then you mentioned a radius can be variable. So potentially if you're looking at a radius smaller than a bucket, you need a bucket smaller than that and smaller than that. Maybe you could try some similar logic.
Yeah. So let me riff on that a second to see if I understand what you're saying, Brian. So what I was proposing at first was if you could let's say, to simplify the problem, right? Let's say we at first only solve the problem for like 8 zoom levels. So let's say you can only query 8 zoom levels. We can always refine this later by taking the zoom level slightly bigger than what you need and then like culling the data set once you solve the problem, right? But let's pretend we have 8 zoom levels. Is the idea that whenever you change a person's position, you would also then go ahead and pre-compute their grid space in all 8 zoom levels, let's say. So I'm in bucket 42 at zoom level 1, bucket 147, zoom level 2, blah, 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 right? And then when you have a query for all the people near me, I figure out which bucket I'm in right now at the zoom level I'm at, and then I query for everybody else in that bucket. Like that would solve everything but the edge case, right? Like where someone's near the edge of a bucket. And you might be able to solve the edge cases by, at any zoom level, deliberately putting me in multiple overlapping buckets. So like the bucket could be like this for like, I'm centered on this bucket. Let's pretend, no, that's not a good example. I'm on the edge of this bucket. Let's pretend, right? And so maybe you log me in bucket 42 at Zoom level 1, but you also log me in this bucket that half overlaps this bucket. You see what I'm saying? And this bucket and this bucket, but it multiplies the amount of data you have to store by 4, because then you have to store the 4 closest buckets that are overlapping that I'm in. But then it makes the query possible without missing anybody that's on the edge. But I'm not sure that satisfies your problem constraint though, because that means 4x the data storage plus 8x based on the total number of buckets anybody falls in, right? And once you find everybody in the bucket, if you want to be hardcore about you being a certain radius from someone, as opposed to being within a 100 yard square, square of that person, you still have to, within that bucket, calculate all the actual trig distances in order to get the people who are literally 100 yards from me, right?
That was a lot. Okay, so you mentioned, if we could do exactly 8 Zoom levels every time you moved, you would compute, the 8 Zoom levels, I guess, centered around that person. So I guess like what can I say is, you could do something like that, but if you did kind of like an infinite level of Zoom levels down to the coordinate, you might not have to keep recomputing anyway, like every time a person moves.
Right.
You can always like do some kind of query that can go down to just the coordinate.
Oh yeah,
precision.
totally. So thanks for that hint. So let me like play it back to you and see if this sounds better, right? Thanks for the hint about the infinitely zoomed in. So given any coordinate that I'm at right now, I can compute the outermost bounds, once again, assuming flat world, because latitude and longitude get distorted as you get toward the North Poles and things get very painful. But let's pretend we're in a flat world and it's a grid that's like rectilinear both ways, all the way through, right? If we were in that world, within my lat long, I can pre-compute the outermost latitude and the outermost longitudes that are within the distance you're querying for. So let's pretend I'm at like 0, 0, like I'm at whatever, Equatorial Guinea or wherever that lands me, right? So I'm at 0, 0, and you want to query everybody within 100 yards of me at this moment. I can figure out the latitude that's east of me, that is 100 yards east, right? And the latitude west, that's 100 yards west, and the longitude east and west, latitude north and south. I can compute those things, and then the query through the database will simply be everybody who falls within that latitude range and within that longitude range are candidates for being close to me. And then I do flat trig on all of them. So that at least means like not much has to be really pre-computed, right?
Well, so you would be doing a trig calculation, like how? Okay, so let's say you are given those coordinates for just that 100 east, west, whatever. Like, so this is what's given to you as your input. What do you do over it to find how many people there are?
To find how many people are there, first we store all the people according to their current latitude and longitude positions. Or maybe lat and long aren't the right, because that's a funny systems with arc seconds and stuff like this. But we convert it into a grid space that we agree on, okay? And we compute their location in that grid space by X and Y. So let's pretend like you're at 3, 4, I'm at like 0, 0. Let's pretend that happens to be the case, right? And then when you say, give me everybody near Philip who's within 100 yards, what I do is I first compute what 100 yards is in our grid system. Like, let's pretend 100 yards is 5 units east-west, okay?
Sure.
So then what I do is I query through all the people in my list for everybody who is less than 5 yards longitude, right? And greater than -5 yards, let's say. And everybody who is less than 5 yards longitude and -5 yards.
Right.
You will happen to fall in that, because we said you were something like 3, 4. You'd happen to fall in that. But once you fall inside that range, I can't be positive that you are literally within 100 yards until I do the final trig calculation of your XY to me.
Sorry, one more time. Wait, why can't you determine why someone's literally within 100 yards of the space you're querying within?
Yeah, because in our flat Earth model, what I've done is I've queried everybody that falls in a square. And that square is technically 100 yards distant from me to its edge. But the problem is if you're near a corner of that square, you are technically more than 100 yards from me.
Oh, I see. Oh, you're thinking of breaking the whole Earth into squares, and then you just happen to be in one of the squares.
Well, I only break it into the square once you tell me how far you want me to query and from whom. So we don't pre-compute what square you're in. We basically only log your XY.
Okay, well, so what will be, so let's say like I don't know, the area you're searching in is n, like just the total number of coordinates of it. Like, what would the time complexity of your solution be?
Yeah. So if the total, you're saying if the total area is n, what would the time complexity be?
Right.
Yeah. Well, I would still be going through, you'd have to query through every person's location. So that's at least O of n when n is the number of people just on the whole Earth. Okay, so you got to do that. And then you reduce it down to only doing the calculus, the actual trig calculations on whatever size your radial distance is, your query distance is, relative to the total area of the Earth. So let's suppose you did say 100 yards, right? Like that would be a tiny, tiny, tiny fraction of the Earth's area. And so it would be that fraction over n is the number of people you'd actually compute the trig on.
Sure. So still n essentially, n divided by some constant.
Some huge number. Yeah.
Right. Okay. We've been a bit into the problem solving. I think if you want to try to code that out, that could be fine. Or how do I push you? Because I actually do have like a direction I kind of want to push you in.
Oh, you absolutely should push me. Like, give me a hint, because you gave me some helpful hints.
Sure.
I would appreciate more hints since I don't know anything about the geospace.
It's really funny because in the beginning you actually said the idea that that would be really relevant for this, but you said you didn't know what it was. It was quad trees.
Well, I can describe to you like a theory of quad trees. What I don't know is how to practice it in this particular case.
Yeah.
So like,
so for a hint though, like you're thinking of the whole Earth at this point. Let's like really simplify it. Okay, let's not think system design at all. You're literally just given Mercer Island. It's just a bunch of coordinates. So with just dealing with Mercer Island now, can you make a data structure of it such that you can query efficiently faster than n time, essentially, not n divided by a constant, just faster than n.
Yeah, well, I can definitely query like if a person, like where a person is, let's say, or whatever, like, because the principle of the quad tree, like if I understand it correctly, right, is like you would take Mercer Island and all the people on it, you know where all of them are right now, right? And what you would do is you would divide it at the highest level, you would divide it into a north half and a south half, as well as an east half and a west half. And you would basically say like where everybody falls relative to that. And then you take each of those quads and you divide them into, a north half and a south half and an east and a west half of that quad, right? And then you go finer and finer until every person is like a leaf node in that tree, right? And then you have their location sort of defined at many levels, basically, through the tree. And so you can stop at any level in the tree and you would have their location within sort of that granularity of where they are. So like, that's as far as I understand with quad trees.
Right.
Like the fine practice of it that I don't understand is if I have two people that happen to fall on two different halves at the highest level of Mercer Island. So like at the, like just bisect Mercer Island east-west, right? And one falls on the east side, one falls on the west side, but they're literally 3 yards from each other. That's the part that I like don't fully understand yet, how to query for that and still know that they fall that close to each other. You know what I mean?
Okay, so if you let's say we ran a recursive operation, so you have like 4 segments now, these 2 people are next to each other, let's say in like the top 2. If you ran like a query on like the bottom segment, what should it return you?
Sorry, can you repeat that question? So these 2 people are actually close, but they're not in the same segment at the topmost level?
Yeah, so if we have A, B, C, and D, I'm just running the coder pad. So one person's in the edge of A, like the right edge, and the other person's on the left edge of B. If we were to query like, and let's say they're the only 2 people on Mercer Island. If we were to query like in this segment, how many people are in there? Like what should we return, or do you have to even look inside it?
Yeah,
mean-
so if you went into, you wouldn't need to go into C or D because there would be no data in the data structure there. So you would know that there are no people in C or D right now.
Depending how you do it, yeah, maybe there's no data, or maybe you've done all
Or
the
you say
calculations,
there's
you
nobody.
completed, yeah, it just says 0. Right, so you can just return there. And then I think you can definitely play with this idea. Like, as in, like, some squares are basically irrelevant, right? So then if you think within, let's say you look within the top quadrant now.
Oh, I get it. Yeah. No, thanks for that hint. That makes a lot of sense. So let's riff on your A-B thing, right? So one guy's on the right side of A, the other guy's on the left side of B, and then there's nobody else on Mercer Island, right?
Yeah.
And the thing is, when I want to know all the people near some guy on the right side of A, let's say, like, what is the total type of tree query I actually have to do before I know that for sure, right? All the people in A, that part's almost the easier, obvious thing, which is like you go down into A, into its quads, you figure out which ones are close to the final guy's destination, and you keep trimming the parts of the tree. Like you only nav the parts of the tree that are still within like a conceivable distance, right, of that. And I think your hint to me is basically you can't eliminate B from the very first step. Because the problem is the A guy could be very close to B, right? The guy on the right side of A happens to be very close to B. So, okay, this is a great hint. Thank you. So like, it feels to me like the traversal of the tree then is something like you know the location of the person the location you're querying from, right? And let's pretend that's the right edge of A. And then you think to yourself, like, what is the query radius? And then you can basically think about that as highlighting all the nodes in the tree you actually conceivably have to navigate. And this, in this case, since we're on the edge of A, it would include B at the topmost level. But if we dive one level into B, right? Like, let's pretend we dive one level into B. And now we're looking at the quad, like the quads in B. You only need to query the left quads in B at this point. And the way you know that is because you've done this radius calculation of like how far or how close you have to be for the queries, right? And so then you navigate, like you basically recursively go down this tree until you've like reached all the nodes, all the leaves basically that are like close, right?
So now that you've kind of thought about how the query actually works, what would the time complexity of a query now be?
It should be a log n query, right? Yeah, it should be. Wow, that was great, Brian. You taught me something. You taught me something live. That's great. We're doing it live. What could possibly go wrong? Okay. So that is very cool. Okay. So then, right. So then the idea is you would first take the list of the people wherever they are. You would put them in the right nodes in the quad tree as at whatever depth is the finest query that you're going to do, right? So you put them in those places. And you can actually make the quad tree sparse, right? Like you could make it sparse potentially and just yeah, well, let me not just say that. Let me actually think that one through. So what would it mean to have a sparse quad tree? So okay, when there's only one person in A and one person in B, let's just say, your quad tree can just have nodes A and B, and they each have one person in them. The moment you add a second person into B, let me think. When do you need to? Okay, now I'm freewheeling. This may be very wrong, but here's the intuition: is you only need to add a new level of quads under B the moment you add a person to B. Let me think. The moment you add a person to B, that would fall in a different quad from the existing person. Is that true?
Are you trying to create a tree that's not sparse?
I'm trying to create a sparse tree. Like,
so why are you being selective of when you're adding someone to something or not?
I guess it really doesn't matter to add a node just whenever you need one for a person, right? And so for the sparse tree, what you would do when you add the second person to B is if they happen to fall in the same Okay, maybe I am not thinking this through correctly. What I was going to propose, and you should correct me on this, Brian, what I was going to propose is that when you have one person in B, obviously you have just the B node and that's that, right? When you add the second person in B, do you only create the quads under B and sift everyone in if the second person is in a different subquad from the first one, or do you always create that?
Right, I'm not really seeing the logic of why you might be selective in creating something or not. So just to kind of finish it, because I feel like I've gone, I mean, if I were interviewing, like I've got a lot of signal when you're problem solving already. So, but basically, like with the quad tree, you said go to the finest amount. So basically, you don't need to be selective of when you fill someone in something or not. Just with your coordinate data, everything has a leaf node, and then its parent will have like how many children or how many people exist within its children, and so on. Right. So you don't need to think of a conditional logic of whether you should include someone in a node or not. With that, I feel like we should maybe try to get Karen real quick. And I'm not sure if it's helpful, but I could just expand on this just for the viewers if someone doesn't get it. But right, so we have like 4 quadrants, let's say. Sorry, this is just taking time, but we can just try to create a quad tree, and actually to simplify it more, because I feel like, we should probably do some code. Instead of thinking of like a list of coordinate data, let's just say we actually have, just let me turn on auto brackets real quick. Auto close brackets. Let's say it's already constructed in a subarray like this. And so each of these points represents whether there's a person or not. 1 is true, 0 is false. Let's see. I'll just make it 4 by 4. So using something like this, I think we can try to kind of break this up into segments like you said. So, right, this top corner is A, then this is B, C, D, right, this is A, B, and so on.
Right.
Yeah. So yeah, we can just, if you could just try to like code a quad tree from this.
Yeah, so then if I think about, and I'm gonna get the types here wrong, but let me think about just the data structure of the node itself, right? Should have, okay, so I'm gonna get this part wrong, but I should be able to define a type, right?
You want to do TypeScript?
Yeah. So let's see.
Just switch over quick. It's on JavaScript right now.
Yeah, and I'm super rusty on this, so we're gonna freewheel it. All right, cool. Great. Nice, check you out. So, so if I have a, or I can do interface, right?
You just make a class that's gonna automatically type for you, like in person.
Oh, do I just do like that?
I think it should infer the type for you. Yeah.
Sorry, Brian. What did you say?
Well, I think if you do a class, it'll infer the type for you, and then also you can reuse it by saying like new Q node.
Awesome. And I'm going to be super rusty on this, but I think what we need is at least something to store nodes that are children, right? So we can basically say like children is like Q node. And it's going to be a list of 4 of these, right? So
Oh, I see. Yeah, I think you do have to type actually, or interface if you're writing them like this.
Oh, right. Sorry.
I thought you were just going to define the properties right here, but if you're literally just writing type, then you have to like interface.
Yeah, then it would be something like this, right?
Right.
Great. So this would be like children would always be 4, and it would always go, let's say, we have a convention, A, B, C, D, the way that you have them listed there. So row first and then column next, right? For the 4 children. And it could be Q node. Let me see. I'm going to get this wrong, but we're going to need don't we need basically a union of Q node and like undefined, something like this, right? Man.
I'm not that advanced in TypeScript yet. I don't even know what union means.
Yeah, no,
I'll take your word
no,
for it.
there's a way to get this done. Okay, but you know what I mean. Like it's going to be QNode or undefined.
Okay, right.
Can like freewheel with this for now. We'll get the proper syntax later, but
Okay.
that's and
Would
then
it be simpler if like instead of undefined you just, well, I guess at the very leaf node you don't have a child, right? I guess that's the only case, but okay, I mean.
yeah, and I am kind of like making this up as we go along, but then you have a UID of, we need to define what a leaf node looks like, right?
Oh no,
And
we
so
only have 10
maybe,
minutes.
what was that? Sorry.
We only have 10 minutes left of coding.
Oh no, never gonna get through this. All right, so yeah, so let's say this is an int or a number, right? And I'm just making this up here. So like in a node where you, in all leaf nodes, you would have the UID of the person that's actually in that leaf node. Does this actually?
Oh, these are only leaf nodes. That's what QNode is? Or
Yeah, yeah. Or
well,
should I
then
actually
they don't have any
different?
children then. I think you can simplify your logic by, let's just make like just a node in general. It can be a leaf node or not. But so essentially children makes sense to me.
Yeah.
I guess you could put UID. I don't think it's important for this challenge.
Yeah.
But like, what do your squares represent? Like, what do they tell you?
Okay.
Like, if you look at a big one.
So let me clarify what you're saying. Is what you're saying that if we go and just have children instead of having UID track, then the existence of any node in there without children at all is by definition a leaf node, and it indicates that someone is there, basically.
You could, so again, I feel like I think you're thinking of it as making like selective leaf nodes. You can make leaf nodes even for things that where no one's there. But if you did something like this, when we're querying, if we're querying just how many people are in some map, and you're at some location you query around you, what's important is each square tells you how many people are in there. So potentially you might need to recurse people or not, but that's an important piece of information, right?
Oh wow. Okay. So can I see if I understand what you're saying? So are you basically saying that nodes can look like
Sure, yeah.
like this basically?
Yeah. Not a number, right? Just a number. Like how many people are in it? Because
Oh,
right now
okay.
we're just
So
seeing...
you mean like literally like a count of people?
Yeah, exactly.
In this location. Okay.
Right. So like,
and then what would happen is you would keep updating this count for all the people under that node, right? So when you add a node, let's say you add someone to the biggest B in the whole quad tree, right? You would add to the people number all the way up the chain to the head of the tree, basically. So that people always represents all the people in that node, all its sub nodes, correct?
Yes.
Okay. All right. Nice. Okay.
And what's the time complexity of that?
What was that?
What's the time complexity of that adding? Or like
that is still log in because whenever you add the tree depth on average, and I like assuming a reasonably balanced tree should I think be log in. Cool.
It's actually a complete tree, so it's always balanced. Right? I mean, if you include all the sparse, if you make it sparse. So it's like log n, where n is just the total number of cells, even if there's no one in them. Right?
Nice. I love that. Like you're teaching me so much stuff, Brian. This is awesome.
I researched it last night, so I wouldn't look stupid today. So
I should interview more with Brian as a way to learn. This is great. Okay, cool. So then, if I understand correctly, whenever we're adding a person, right, we basically add them to whatever depth of the quad tree we want to get the finest granularity location that we want for that person.
Or again, let's just add them to literally the finest. Let's not make it a variable like how deep we want to go. So every single 0, 0 has a leaf node. Like every single coordinate has one node for it, right?
Yeah, for the grid that you've shown here, basically.
Right.
Okie doke. Cool. So then now we want to build a tree out of the map, right?
Yeah. Right.
Cool. And then it's the map would be like, I don't know, something like that.
Yeah.
Right. And so what we want to do is go through and for let's see, for each row and column. So And we want to return the head of the tree, right? Syntactically, this smells funny.
If you don't want to worry too much about typing, I think that'd be fine. So we have like 5 minutes left anyway. We could even just talk. I don't know. But
yeah. So okay, so we want to go through each row and each column, adding but at the right depth. So
the root represents this whole thing, right? Like how many people are in it. And so in every node, including the root, you have 4 children potentially. So like, what would A encompass? If the root encompasses all this, what does A encompass?
A in this case?
Yep.
Yeah, is just this guy right here, right? Or do you mean the big A?
Right, right.
The big A is these 4 zeros, right?
Exactly. Yep.
Yeah. So
you can probably see some kind of recursive logic too, because for this big A of these 4 zeros, that's A. So AA is its, top left. So then that'd be like just 0.
Right. Okay, I need to think about this a little bit. So if we went through, okay, like the lame way to do this would be to go through at the row and column level, adding the first level of, accounting for the first level of nodes at all. Like this.
If you went through, like, are you talking about like go 1 by 1 kind of? And add them in?
Right.
That'd be, well, that wouldn't, well, you could, I guess, but your true, I guess the complexity of making your tree would be huge. I really want to steer you on this. It's just like, so what you could say is, if you thought of this as like start X, let's say it starts at 0 because it goes from the left side and it goes to the end side, right?
Yeah.
And X is length, right? And then same with Y, start Y is 0 and Y is length. Then if you think of just its A quadrant, what's its start and for each?
Yeah, it would start at 0, but end at basically inclusive at 1, but exclusive at 2, right?
And the total, the first end is 3, right? And then so just as A quadrant, it should start at 0 and end at you said 1 or 2. I mean, it doesn't really matter, but 1 makes more sense to me. So like, how can you tell it to make its A go from that?
Yeah, so
Like 2 minutes.
The
pressure.
So painful.
Let me throw in params for you. You can throw in the start and end X over here. Basically, like if you kind of pass it down, you can say this first one, right, encompasses this range. Then you can start to think about what ranges children would be in.
Oh, so you're saying basically have coordinates, have build tree be the recursive function, and so you'd have something like start X, start Y, like that.
That's how I'll do it.
End X, end Y. And then the main, and I'm not going to type it with all the numbers right now, but the main call would be something like tree would equal build tree map, right? 0, 0, like you do something like this.
Yeah, sure.
Okay. And then the question is like, how do yeah, but if you do that right, okay, great. Okay, that was very helpful, right? So so then you would have something like node so node equals, and then okay, so you would have to go through the start and end X and count the number of people in there, right? So hold on, so
maybe we should talk about that more, but so you're thinking about counting the people at this level, but actually you could just have your children return to
you should just recurse in, right? Shouldn't you? So so you'd want children so painful. So let's think about the, you want to recurse in. So if, right, so the base case would be if index, let's say we said 0 and 3, so that's inclusive of the end. So if start x equals end x and start y and y. So I'm just trying to end the recursion here, and the theory here is if I am at the finest level that the tree could possibly get to, then the thing that I should return is just the just the people would be like, essentially the people would be 1, right?
Oh, maybe.
People,
Well,
the people would be
because if you look
m.
at your map, it's only 1 if the map thing is 1. Otherwise, there's no one there.
Yeah. So like the people would technically be m's like start x, right? Something like this.
Yeah.
Right. And then the children would be none, basically, for this, right?
Sure.
Would be something crazy like that. And so we just need to return a
looks like we're at time, actually.
Yeah.
Oh, wait, Kelly says 1 minute left. I'm sorry. I'm tripping you out.
I'm sorry, we should have gotten this done, but essentially you'd want to return something that where the children, would be empty, right?
Yeah.
Something like that is what you want to end up returning. And then the recursive one is basically in all other cases, you want to basically find the midpoint. So you'd want to recurse down in the 4 cases, right? Where you want to do essentially end x minus start x divided by 2 for before that.
That's it.
For that, right? And go through all 4 kids. So
yeah.
Sorry we couldn't jam through all of that.
I mean, that's okay. Honestly, like, even though you didn't code it all out, like, what you're saying is exactly how you do it, and then code is just writing. But if we stop there and, like, I guess feedback time is now Kelly, or Kelly's coming on.
Yeah, hi. What a ride that was. Past for 50 minutes. So, Philip, if you can reflect on your performance.
Yeah, I felt like this went pretty poorly. I felt like if I could be more articulate about the things that went poorly, I think I overthought the complexity of the problem at first, and Brian's multiple hints to me to like go straight down to the like an infinite grid level where you're basically at the point. That was very helpful, but it took probably 10-15 minutes before I could get myself to not over complexifying this problem. So I felt like I made it overly complex. I was clearly rusty in the coding of things itself, like flipping to TypeScript and not being able to whip out the proper TypeScript was like a fail. And so that was bad. I thought that my another example of overcomplicating, what Brian really helped simplify, is like the fact that I knew that Earth distance is a bunch of trig stuff to calculate for the spheres. That's like way too complicated relative to where we wanted to get to with this problem ultimately. And like Brian, with this solution, like we still wouldn't have solved the problem that the longitude lines get closer and closer as we get to the North Pole, and like funny things happen, right? But this is still like really helpful to me. So I felt those were the things that stood out to me as being obviously not as good and things that could improve. Curious, Brian, what you think?
Yeah, first of all, I literally had no idea about longitude and latitude lines getting closer. I actually don't know that much about spatial stuff. I literally just looked up. Anyway, I think so. You did over complexify in the first part. What's interesting is like, so like I'm a junior software engineer, so like for that would be a bad thing. I'm not, but like it's pretty impressive how much you know at like at a very high level. So I feel like you probably do a lot better for, that's just my guess, for higher role interviews. I thought you're actually very fast at problem solving, and you took hints pretty well actually. I think it's true it did take us a while to get to the granularity kind of concepts. However, like you're really fast with coming up with new ideas. So I thought in problem solving wise, I think you're really strong. And in the code, it's true you're a little rusty. However, like when you talk about the concepts, you do a lot better than most people, I think. So like you just you know the concepts in English, you're rusty in like writing it out into code. But the actual English was like super fast. So I thought, I don't know. Maybe that counts as problem solving. It counts, to me, it counts as like 75% code. And the 25% code is actually writing the code, in my opinion. Those are my main impressions.
Phil,
Yeah.
what did you, how, do you have any feedback for Brian on how he conducted the interview? I know you've done a lot of interviews over the years. So how do you do?
Oh, I felt that Brian did really well. I think he was very gracious in correcting me when I was obviously veering off the road in the wrong direction. I really like, for instance, Brian, how you typed out the ABCD and the grid over here in a way where I think both you and I might have already had that concept in the mind, but I do think in cases of people listening in, as well as in other engineers, like it might not have been clear in their head that that was what was going on, you know? So I felt like that was very useful. I thought that in some cases, you know, this experience was really great for me because I volunteer with Formation hosting the Algo mocks several times a week, but it's good to be reminded how sometimes a problem later that I will no doubt feel was super easy and I just messed it up, will in real time feel like it's time pressure and very difficult to think on one's feet, right, in real time. So I definitely felt like you did a good job being gracious about that and leading us through the problem solution.
Thanks. Do you want my feedback on how I did too? Because like as an interviewer, because I feel like I probably should. I feel like I didn't focus enough on the code at first because Philip has really strong system design skills. So he was talking about like an earthing at first, and I probably like should have said something sooner. And other than that, I also like accidentally threw out the idea of quadrate, but he already said it, so maybe that's not such a big fumble. I'm not really sure.
Does anyone online have any questions for Brian or Phil? All right. Phil, you mentioned how Brian was gracious in the hints. Like, is that something that happens often in these types of interviews? Do your interviewers kind of help you, get to a place where you can solve it, or does it really just depend on who your interviewer is?
In my experience, it depends a whole lot. Like, I feel like the folks who aren't very strategic about interviewing, they might often approach the interview as almost an adversary relationship. You know what I mean? Where like you're the guy quizzing and it's like the Inquisition, except without the religion, it feels like that. But I think a lot of times when I interview, I love to approach it in a way where it feels like we're together trying to get to a solution. And what I'm trying to figure out is how much of a crutch do I need to provide in order for us to arrive at the end, you know what I mean? And what I'm gauging by the end of it, because I like to leave interviewees, no matter what, feeling like if you've ever done an escape room, right? Like if you've only done it a few times, like you have no idea the guy on the microphone is always trying to hint so that you can escape by the end because they want a satisfied customer who gets out at 59 minutes, But what only he or she knows, the actual dungeon master or whatever knows, is how much hinting you needed relative to the average person, And that's where I'm trying to get to, where by the end of the hour, the person always feels a small success, like they landed the thing, blah, blah, blah. But I have a good gauge for how much hinting they required relative to the average candidate.
Got it. Well, thank you both. This was really, really awesome. Great job, Brian. Great job, Phil.
Yeah, and thank you, Brian. This was a lot of fun, and I am glad I had a chance to slightly embarrass myself. So it only serves me right. So great. Thanks for your time today.
Yeah, okay, come by, visit the Statsig office sometime. You're like 8 miles away, right? And I'm here now, so. And you just said you have like prank stories at Meta too, so you have to come
awesome. Great. Thanks a lot, everyone.
All right. Thanks all. Thanks
Take
for joining us.
care. Bye-bye now.